You may have heard that modern electronic devices are made from semiconductors. Semiconductors, like silicon, are materials that are not quite as electrically conductive as a metal, like gold or silver, but they're also not electrically insulating like glass. So, to understand the properties of these modern electronic devices, we need to understand semiconductor physics. And we'll start then our journey into the fascinating world of semiconductor physics by learning a few key concepts. In the following 4 slides, we will introduce 4 concepts: energy bands, band diagrams, electrical carriers, namely electrons and holes, and doping, which is the ability to add electrons and holes to a semiconductor to make it do exactly what we want. You may have learned that when atoms are far away from each other, so that they cannot interact with other atoms, they absorb or emit very specific packets of energy. These allowed energy packets are defined by what we call energy levels. As we bring atoms closer and closer to each other so they can interact, these energy levels overlap and they form what we call energy bands. In semiconductors like crystalline silicon, the lower band is called the valence band and the higher band is called the conduction band. The energy gap between the 2 bands is called the band gap energy. Now, let's focus on the energy bands and gaps for crystalline silicon. Let's imagine for a moment that we have an infinitely thin slice of silicon, and we're going to plot 2 very important points in the energy axis, the vertical axis. We're going to plot EV, the top of the valence band, and another point for EC, the bottom of the conduction band. The energy space between EC and EV is what we call the band gap. Now, we're going to stretch this thin slice into a long slab, and there you go. You have a band diagram. A band diagram shows key electron energy levels as a function of a spatial dimension in a semiconductor. So your horizontal axis is either the thickness or the width or the depth of your semiconductor. The band diagram shows the top of the valence band, the bottom of the conduction band, and sometimes it shows explicitly the energy band gap, e.g. It also always contains the Fermi level, a concept that we're going to learn in the course that describes the distribution of electrons in a system. When we look a little bit closer into the conduction and valence band, we realize that most of the electrons that are free to move are in the conduction band, and then we have an almost empty valence band. Electrons are really the only particles that are available for transporting energy, electricity in the semiconductor. So we keep very good track of them when they are in the conduction band. However, in the valence band, it is actually much easier to keep track of the places where the electrons are not. So we call the space where the electrons are not, or where the electrons have left, holes. Once we start counting the number of electrons and holes that are available for conduction, you realize that there are very few electrons and holes in what we call an intrinsic semiconductor. This is a pure semiconductor that only has the atoms that composes them. In this case, for example, silicon. It's amazing to find out that even though we have 5 times 10 to the 22 atoms per cubic centimeter, there are only 10 to the 10 free electrons on the same volume. That means 12 orders of magnitude less electrons and holes compared to the number of atoms. But fear not, it is relatively easy to add impurities to silicon, so we can change the number of electrons and holes by 11 orders of magnitude, going from about 10 to the 10 per cubic centimeter all the way to 10 to the 21. So how do we do this? Well, in the case of silicon, we can use something like phosphorus, which adds free electrons, making the silicon what we call N-type. If we add boron, on the other hand, then we add free holes, and this makes the silicon p-type. So by combining then N-type and p-type regions, we can make just about any type of electronic device, like for example diodes or solar cells or transistors. Okay, that's been a lot of information, so it's time to summarize. We learned that energy bands appear from bringing atoms together into a crystal. We use this information from the energy bands to form what we call the band diagram, which shows key electron energy levels as a function of a spatial dimension in the semiconductor. We also learned about holes in the valence band and electrons in the conduction band. We also learned that even though there are very few electrons and holes available for conduction in an intrinsic or pure semiconductor, it is relatively easy to add impurities to the semiconductor to change the number of free electrons and holes. We call this doping. Okay, it's time to take in all this information and make it yours. I'll see you at the lecture.